question, you're going to want to repeat them.
I will repeat the questions, and if you get any questions over the street,
Yeah, sure.
on Piazza, let me know. So, all right, everyone, let's start. So, hopefully this room is better. I'm glad that you don't have to climb over each other just to get to a seat. First off, let me introduce to you a new professor, Professor Thomas Manzini. Tom, do you mind?
Not professor.
Well, next week, all right. So I'm going to be off in Israel next week. So Tom's going to be conducting the classes next week, and we will be covering backpropagation and some techniques for optimization when you're training networks. I should be back the week after, and so the next Monday will be me. Thanks, Tom.
Do you want to That's probably a good idea.
What? This is Tom.
Hello. I'll stand in front of the camera as opposed to
Yes.
standing behind it.
Yep.
Pleasure mutual.
And we should be posting T hours. Have you done that already?
We know them. They're not on the course page yet. So this Friday, right after recitation until noon, we'll have office hours. And then next week, regular hours will start from on Tuesdays from 3:30 to 5, and then once again on Friday after recitation. And then, of course, if you guys need help, we can be around. Send an email.
And we're pretty prompt on Piazza most times, unless it has to do with logistics, which we can't deal with, at which point we just pretend you didn't ask, right? Hopefully this class solves problems both in terms of seating and in terms of being able to stream. So those of you who are watching on the camera, please let us know. Just post on Piazza if there are any problems. We've got new recording audio equipment, a new camera, and a new classroom where I can actually draw on the board, write on the board, and you can see it, and you can see what's on the screen. So have we already put up homework 1? If we haven't, we will be putting up homework 1 today.
It's released.
It's released. The part 2 is also done. Kaggle? Okay. So you must have got the link to homework 1. Those of you who haven't, the link to it will be put up on the course pages, so you can always get to it. The first part will be scored by AutoLab. The second part is one where you will be training a multi-layer perceptron to recognize speech, and you will be competing with each other on Kaggle. That includes everybody in this room and the people who are watching on camera and the people who watch this video. Everybody who's registered to class, part 2 of homework 1 is going to be on Kaggle. All right. So let me begin with today's class. We're going to deal today and for the next 4 classes with the problem of learning in neural networks, multi-layer perceptrons. We'll look at the problem of learning, the perceptron rule. We'll skip one topic, but it's going to turn up in your quiz, and we'll look at the basics of empirical risk minimization. Through the class today and in future lectures too, I'll keep sort of taking side little branches off to the side to talk about basic things like calculus, like matrix algebra, stuff that you're supposed to know that we think it might be worth spending 5 minutes revisiting, right? So here's a quick recap. Neural networks are universal function approximators. They can model any Boolean function. They can model any classification boundary. They can model any continuous valued function. We've already seen this in the last class. Provided the network satisfies minimal architectural constraints. We also saw that if the network was missing even one neuron, it could you could end up in a situation where the function was essentially not modelable at all, right? Now, the whole problem of AI, we have tasks such as these. You have a voice signal coming in, you have transcription coming out. An image goes in, text captions come out. Game state goes in, the next game state comes out. All of these boxes, they are really just functions. And because a neural network can model any function at all, as we just saw, we expect that the neural network can model all of these functions as well. So, which is why they're so popular, right? The questions here, I have a function. What is a function? It maps from the input space to the output space. So something goes into the function and something comes out of the function. The questions we must answer: what is it that goes into the function? How do we represent the input? We are speaking of text, images, whatnot, game state. That is not very clear. We have to define that. How do we represent the output? There must be transcriptions. There must be game state. So the representation of the inputs and outputs is a key problem that we will deal with later. What we are going to deal with today in today's class is how we compose the network that performs this function. Okay? Back there, if you don't have a chair, maybe you can just come out in front, right? You need to be able to see. There is a chair up here in front. Okay. So again, recap. The units in the network are perceptrons, as we saw. They take in weighted combinations of inputs and a bias term, and the weighted combination of the input plus the bias must exceed a threshold for it to fire. That is the basic perceptron. But the activation here need not be a threshold. It can be any function at all. So the weighted combination of inputs and the bias, that can go into any function sigma, and you can get an output. And the function sigma, various forms of the function sigma that we saw in the last class included the threshold, the sigmoid, something that we call the rectified linear unit, and so on. Now, just as a matter of notation, here I have several inputs. Each input is combined, multiplied by a weight, and then they are added, and then there's an extra bias. I can replace that equivalently by extending my input by an extra component whose value is always 1, in which case the bias just becomes a weight. This is just a matter of convenience in notation, nothing more. So I don't have to explicitly write plus b each time. So anytime, I'm going to kind of switch back and forth because it's hard to stay consistent over thousands of slides. But anytime you see an equation of this kind, which does not explicitly include the bias, in your mind you must immediately assume that I have extended the input by a single constant 1, and the bias is now just an additional weight. So that's just a representational for convenience. I'm going to be using it on and off through the course. Now, the structure of the network, for now we're going to assume a feed-forward network. What I mean by that is that when the input comes in, each unit processes it and passes it down to additional units. Anytime a unit is done processing some data, it's never going to revisit the data. So the data keeps flowing forward. If I view this as a graph, this is a directed acyclic graph. There are no cycles. And the entire business of cycles we will deal with somewhat later in the course. So the actual structure of this graph itself, for today we're going to assume that this network is capable of modeling whatever function we want it to represent. Exactly how we will arrive at that structure is not going to be part of the next 4 lectures. We are assuming that you're given an architecture. How do we, this architecture can represent the function that you want, but then the network has these extra parameters. How do you set it so that it represents the function that you want? So here is the abstract notion. There's an input x, there's an output y. The network is just a function f which operates on x to give you y. The parameters of the network, they are the weights of all of these edges and the biases. And by learning the network, what we mean is how do we set these weights and these biases for the network to compute the function that you want it to compute. So moving on, we said the MLP can be constructed to represent anything. So I can take any odd function. Here I have a 2-dimensional input. The function is this blue sheet. And I want to compose a multilayer perceptron that can compute the function represented by this blue sheet. How do I do it? Now, for a simple function of this kind, where I want the output to be 1 inside the function, this diamond, and 0 outside, we know exactly how to do it. You can just hand draw the network. You'd need 1 perceptron for each of the 4 edges. You need an OR, you're done, right? The problem is that for all but the simplest problems, this is really not going to be possible. You have to do something more. You have to learn. You have to estimate the network. So let's say you're given the entire function g of x, where x is the input. The network itself represents a function f with parameters w, where the w are the weights of the network. And our business is to figure out how to set the weights w such that this network represents this function g. And the way we can do it, I can define an error between the output of the network at each x and the value of the function I want at that x, right? So this div is a divergence function, which basically measures the error between the output of the network, which is this term, which is a function of the weights, and the desired output g of x, which is given by this guy. Now, so if I were to draw this, for any given weight, for if this is x, guys on camera, let us know if the figures are too small for you, right? If this is x, if this is x, if this is y, I'm just going to represent the output as y, and let's say this is g, so g of x, then for any particular setting of w, I'm going to get some figure, right? So for one setting of w, maybe I get this function. So this is f of x semicolon w1. For a different setting of weights, I will get a different function like so, which is f of x semicolon w2. So for each setting of the weights, I'm going to get a different function. And I want to find the weights for which the function exactly follows the red line. Now what this means, the way I can do it is that I can define some measure of the difference between what I want and what I get, and this is a function of the weights itself. I can choose the weights that minimizes this error, so which is to say I'm minimizing the total error across all x, and I'm finding the weights that minimize this total error. If I do this, this is just standard function estimation, function approximation. I should be able to find the weights for the network that best represent this function. Questions, anyone? Right, this is basic stuff, right? Nothing new. Okay. Now, the problem for this, to use this approach, you need the function g. It must be specified everywhere. And the problem is, in practice, you are not really going to be given this function g everywhere. What you will be given instead is a bunch of samples. So that's the function g that you want to estimate. But what you will be given is a bunch of input-output pairs, x's and the corresponding values y. Several of these. So what you will actually see are just these guys, the xy pairs. And collecting such samples is fairly straightforward, right? For example, if you're trying to classify images, this is like the x would be the images, the y would be the class label. If you're trying to recognize speech, the x would be the speech signal, the y is going to be the transcription. Collecting samples is easy. Specifying the entire function is not going to be possible. So what we will get is collections of these samples, and we are going to have to estimate the function f such that at least at these samples, the output of the function matches the y that you actually got. And you hope, at this point, it's a hope, that if I do so, if I fit the function properly at all of these red dots, in the rest of the space too, the function is properly fitted, that it's actually giving you what you really want. This is what we're really setting about to do, right? Now, let's start with a very simple task. So this looks complex. I gave you a very simplified picture. If you look at, in reality, when you go up in high dimensions, it becomes really complex. So let's start with a very simple task of learning a function. We'll learn a specific kind of function. We'll learn a classifier, because classifiers have quantized outputs. They're much simpler than regressions. And also because this was among the earliest problems addressed using MLPs. Specifically, we are going to consider a binary classifier. Is this x or is this not x? So remember, we've seen examples of binary classifiers. Does the input lie within this polygon, or does it not lie within this polygon? That's a binary classifier, right? So we will use this. Now the original MLP is a network of threshold units as it was originally defined. So I'm going to walk through history. I just said that in a perceptron, the activation function can be anything. I'm going to walk back several steps, and I'm going to go back to the simplest definition of the perceptron, where the activation function was a threshold function. So each of these units is now a perceptron with a threshold activation. And the simplest such network that you can think of has only one unit, right? Just a simple perceptron. So let's try to learn just a single perceptron that can classify, that can learn to classify between elements. So this perceptron is a step function. It has a linear decision boundary. And if you have two classes which are separated by a line, I can try to estimate, I can learn it. Specifically, when I say I want to learn a perceptron, I want to learn this function, what is shown on the screen, except what will happen is that you're not given the entire function for you to learn the perceptron. You're only given a few samples. So you're going to be given those blue dots and those red dots, and you're going to have to learn the perceptron. So now here's what we have. We are given a bunch of input-output pairs. The perceptron itself looks something like this. Y equals 1 if the weighted sum of inputs exceeds a bias. It's 0 otherwise. So what do we mean by saying by learning a perceptron? We mean that we want to learn the weights W and the bias B such that the perceptron on these dots, it gives you a 0 for these guys and a 1 for these guys, or whatever, regardless of how you define it. Now I can restate. I'm going to restate the problem differently. I'm going to go back to not having a separate bias. I'm extending the input by a 1 so that I can treat the bias as a weight, and this is what we'll work with. This is just for simplification. Now before I continue, here is let's just a little bit of, do we have the, yeah. So the equation for a hyperplane. Can anybody tell me what the equation for a hyperplane is? Anyone? Standard equation for a hyperplane. Y equals mx plus b. What is m and what is x? That's a line. I'm speaking of a hyperplane, right? Anyone else? So here's how it is, right? If I say W transpose x equals 0, then if I think of the space, so let's say this is my vector W. What x's does this equation represent? Anyone? Not just line. It represents every x that's orthogonal to W. Correct? So if I say that, we are saying x is orthogonal to W. That's the only constraint that you're imposing over here. So when you say W transpose x equals 0, this is W. X is going to be anything, any vector on this plane, because any vector on this plane is at 90 degrees to this W, right? Now, suppose on top of this, I want to have, so this represents this line. Yeah. This represents this line in this case. It goes through the origin. In higher dimensions, it's going to represent a hyperplane, correct? So suppose I have a vector x over here, or let me call this x1. There's the eraser. So suppose I have a vector x1 over here. What will W transpose x1 be? Can you tell me? In this case? Why? Anyone? So here's how I can write this. I can call this point the sum of this vector, which is on the plane, plus a second vector, which is parallel to W. Correct? So I can write x1 equals some x plane, some vector on the plane, plus alpha times W, correct? Which is in the direction of W, and alpha is a positive number. So in this case, W transpose x1 is going to be W transpose x plane plus alpha times norm of W squared. Correct? And what is W transpose x plane? That's 0. Alpha is a positive number. Norm of W squared is positive. So any vector which lies in the same direction as W, but off the plane, W transpose x is going to be a positive number. Correct? Now suppose I have another vector x2 out here. What will W transpose x2 be? It will be negative because I can write x2 as some other point on the plane plus this guy, which is also parallel to w, but in the other direction, right? So I can write it as x plane minus alpha times w. So w transpose x2 is going to be 0 plus minus alpha times norm of w. That's going to be negative, right? So simply for any point, I can simply check the sign of w transpose x and tell you whether it's in the direction of w or opposite to the direction of w, whether it's on one side of the plane or on the other side. Very simple. So let's get back to our problem. Our problem is we want to find the weight w such that this weighted sum equals 0. In other words, w transpose x equals 0. That's the line, right? And you want this plane to perfectly separate the two groups of points. So what do we really want? We want w transpose x to be positive for all of these green guys and negative for all of the red guys. So given this, in which direction do you expect w to point? Anyone? Towards the greens, right? And exactly opposite to the w's. So that's what we want to find. Now, here is the Perceptron Learning algorithm. Here we are using a +1 -1 representation for the classes as opposed to 1 0. You initialize the w somehow. You cycle through the training examples, and as you cycle through the training examples, you're going to classify each of the training examples. Some of these using just the simple rule, sign of w transpose x, right? Some of these training examples are going to be correctly classified. Some will be incorrectly classified. Anytime you get an incorrectly classified training instance, you're just going to increment w by saying w equals w plus y, which is the desired class for the input, times x. Now, what exactly is this doing? So let's go back once again and consider this simple example. So suppose I have a vector, and this is my x, and this is a +1 class. What is the best possible value for w in this case? I just have one vector x. It belongs to the positive class. What value of w absolutely guarantees that it's going to be classified as positive? W must directly point at x, right? In which case this is the hyperplane. It's at 90 degrees. You're guaranteed that w is on the proper side of x, right? Now, on the other hand, if I have a different instance, x, and here I want this x. The screen has gone off. What happened? Oh no, I think I did something here. So suppose I want this instance of x to always be negative. Which direction do I want w to point in? The exact opposite side, right? So this is my vector, so I want w to be this way. This is the plane. This is guaranteed to be negative. So you see what we are doing over here. For positive instances, you want w to point at the instance. For negative instances, you want w to point away from the instance. So it's a very simple, trivial piece of logic. So let's go back and see how this perceptron classification rule works. I initialize my w. Some positive instance of x is misclassified, right? So I'm just adding x to w because I want w to point in the direction of x when x is positive. Some negative instance of x is being misclassified. I subtract x from w because I want x to point exactly, I want w to point exactly in the opposite direction of x. So the logic is really, really simple. And here's how the whole thing operates. So let's say I started off with this random initial, these are the red and the green dots. Green dots are 1s, red dots are -1s. I start off with this random initialization of w, which is this guy. So the red line represents the hyperplane which is orthogonal to W, which is my nominal classifier, and this is the initialization. This instance, which is positive, is on the wrong side of the boundary. That's the vector that's being misclassified. So what I will do is I will add that vector to W, and when I add the vector to W, this becomes my new W, and my classifier boundary swings around and becomes like so. But then now I have an issue. This instance is misclassified, so that's the vector that's misclassified. I will subtract, so I'm pulling W down, and watch how W now, the plane now swings around the misclassified point, and now it gets properly classified. Right? It's a very simple, trivial learning algorithm, the Perceptron Learning rule, very popular too. And the nice thing is that, at this point, the classification is perfect. There are no more updates. It's guaranteed to converge. If the classes can be linearly separated, it's guaranteed to converge in a finite number of steps. And finite in a very strictly defined way. If you have a bunch of training points, if R, and this convergence is usually specified when the initial value of the convergence proof is specified when the initial value of W is 0, it works anyway, regardless of how you initialize it. You just have to modify things. Now, so assume if you initialize W with 0, then the algorithm is guaranteed to converge after no more than R over gamma squared misclassifications, where R is the distance of the farthest training point from the origin, and gamma is the distance of the closest training point, the best case distance of the closest training point from the decision boundary, what we will call the margin in the case of support vector machines. So this is a provable result. So clearly, if I have linearly separable classes, a single perceptron is trivially able to learn to classify it. The Perceptron Learning algorithm is very easy to understand. Why can't I use it here? Right? We know that for this decision boundary, I can build a multi-layer perceptron that will classify this perfectly. Now, what would the problem be? The problem is, even if I use the perfect architecture for the MLP, some information is missing. All of these neurons are actually linear classifiers. They're learning lines. And if you consider this neuron is learning this line. For this neuron, the labeling you will require is what is given over here. Everything above the line must be labeled red. Everything below the line must be labeled blue. But that's not the labeling we have. This is the labeling that we have. So the problem is, we have, as far as that one perceptron is concerned, all of those starred points are mislabeled. So here you have something. If you want to learn this multi-layer perceptron, you actually have to learn how the entire training set must be labeled for every perceptron in your MLP. So it's not like somebody's given you the labeling anymore. If you go back, the labeling is wrong. So you have to figure out how to label the perceptron, the training instances for each perceptron, such that when each of those perceptrons is trained, their combined output will give you the correct classification boundary. And clearly, this is infeasible. You're going to have to search through every possible combination. This is a combinatorial optimization problem. This is a problem in NP. It has exponential complexity. We cannot do this. So, you get it? Right? So the Perceptron Learning algorithm cannot be directly used to learn an MLP because you have this exponential complexity of assigning intermediate labels, even when the classes are perfectly separable. When the classes are not actually separable, it gets worse. So this was some kind of an impasse, and people came up with greedy algorithms, Adeline and Madeline by Bernie Widrow. I'm not going to talk about them. They are on the slides. They will appear in the quiz. So please look them up. They're really cute algorithms. And who's that? Matt back there has had the pleasure of being stolen from CMU by Bernie Widrow himself. Now, so the realization that training an entire multi-layer perceptron is a combinatorial optimization problem that cannot be solved trivially, basically stalled any progress in the research on neural networks for well over a decade, till people figured out what the problem really was. And the problem has to do with this. Now consider this guy. Let's say this red line is my initial guess. The thick brown line is my initial guess for the classifier, right? That has a weight. Now it's misclassifying this red dot. That's misclassifying this red dot, okay? Now I can keep changing that weight. I can keep changing that weight a whole lot. And as I keep changing the weight, does the classification error go down? It doesn't. I can swing the weight all the way down here or all the way up here until it comes here, and the classification error doesn't change at all. And then when the moment I cross that one misclassified point, everything changes. It says your classification error is better. So when I am modifying the weight, I get no hint at all about whether I'm moving in the correct direction or not. So if I were to try to sort of gently, without actually, gently move this thing around and, see if moving it right is a good thing to do or moving it left is a good thing to do, I get no indication about whether it's good or not. I have to swing it a whole lot till it hits that point, at which point I get to know. So this means there is no way for for us to evaluate incremental corrections. And this gets much worse when you go past. For a single perceptron, it was kind of obvious, right? If I give you this problem, there's no way for me to say whether moving the weights for any intermediate perceptron a little bit is actually improving the error or whether it's getting worse. Because we have this problem, you can swing things a whole lot and the output doesn't really change. So in other words, the simple multilayer perceptron is essentially a non-differentiable function. What I mean by that is that the derivatives are zero most places, and there are places where the derivatives are not defined. You can change these values a whole lot and not get any indication as to whether the change that you've imposed is helping you or not. So what we really need, there's a second problem. We assume the data are linearly separable or they're classifier separable. In real life, data are rarely clean. Even they're not linearly, they are not separable. And even for data where the optimal classifier is a linear classifier, they may not be linearly separable. So here, for example, the best possible classifier is a line, but then you have red dots on the green side and green dots on the red side. So Rosenblatt's perceptron wouldn't work here. The perceptron rule wouldn't work here in the first place. So how do we actually learn this? Instead of having a threshold function of that kind, we are now going to change the threshold function by something softer. So for example, let's say I have my let's say I have this this situation where this is a +1, but my classifier calls this side -1, right? So that one training instance is being misclassified. I want to come up with a function where if I rotate this guy to this angle, so if I swing it around, I want to say, yes, you're still misclassifying the instance, but you're misclassifying the instance a little less. And what happens when you've got so if you compare the threshold function versus so swinging the weight is the equivalent of sliding your threshold function. This is the misclassified training instance. If you have a threshold, if I slide the threshold function left or right, the gap this error does not change. This error stays fixed regardless of whether I slide the threshold function left or right. On the other hand, if I use a sigmoid, my sigmoid is like so. Well, it would stop here. if I move my sigmoid left and right, the gap between the desired value and the output of the sigmoid also changes, and it tells me which way I must move my sigmoid for me to do a better job of classifying the training instance. And so now I can be aided in actually learning my classifier, correct? So that's what we're going to take advantage of. We're going to be looking at sigmoids, the one in the second second block. Now the sigmoid, which is this guy here. Now the sigmoid in particular has a very nice interpretation, and that is this. Now consider again a training instance, a problem where the optimal classifier is a linear classifier. So you want a function of this kind, except now the classification is not perfect, it's somewhat fuzzy. So you have a few red instances on the blue side, you have a few blue instances on the red side. So the red instances are at 1, the blue instances are at 0. Now if I look at a one-dimensional example, this is what it's going to look like. Here are all the blue values, the output is 0. Here are all the red values, the output is 1. They are not separable. Now the input is one-dimensional. Because the input is one-dimensional, the optimal classifier is a threshold. I just have to say, anything to the right of this guy is 1, anything to the left is 0. There is no threshold that will perfectly classify both instances. But let's look at things slightly differently. Let's look at each point. Let's look at a small window around that point and plot the average value of points within that window. The average value of points within the window is still 0 over here, right? As I keep going right, the average value stays 0. At some point, the red points begin to kick in, and then the average value keeps going up, and eventually this is the kind of value you're going to see. So that's the curve, right? The sigmoid is actually capturing this guy, the one that we saw. So the sigmoid is actually approximating the probability of the class 1 at each instance, at each value of x. Make sense to you? Right? So the sigmoid is a really nice function which we will encounter later in class. It's based on the fact that as you go from left to right, the probability of class 1 increases. So class 1 becomes increasingly probable as you go from left to right. If x is a two-dimensional variable, it's the same plot, except now it's going to be a sheet, right? Now we'll return to the fact that perceptrons with sigmoid activations actually model class probabilities in a later lecture. Let's move on for now. Now let's look at perceptrons with differentiable activation functions. So this term over here is no longer a threshold. It's a function that can be differentiated. And now I'm magically just tossing out this word differentiated. So we're going to revisit what we mean by differentiable, and we're going to revisit it both in this class and in Tom's class next week. So what we mean by saying sigma z, so the input to the activation function is a weighted combination of all of the inputs plus a bias. Let me call that z. And the output is this function sigma applied to z. So when I say sigma z is differentiable, I can say it means that d sigma over dz is defined for all values of z. Now using the chain rule, now that means I can also take the derivative of y, the output of the perceptron with respect to any of the weights, or even with respect to any of the inputs. So again, what is this derivative actually going to be computing? It's going to tell me if I change this guy just a teeny weeny bit, how will the output change, right? So the chain rule says dy over dwi equals dy over dz times dz over dwi, which just gives you this, the derivative of sigma times x. Similarly, dy over dx is the derivative of sigma times w. Easy enough, chain rule. Now, this means I can compute the change in the output for a small change of anything at the input, any weight or any input, right? And if I can do this for one perceptron, I can do this for every single term in a network of perceptrons. So this means that I can take the derivative of y with respect to these weights, I can take the derivative of y with respect to the outputs of the neurons at the uppermost layer. I can take the derivative of y with respect to the weights just going into those neurons. I can take the derivative of y with respect to the outputs of these guys. I can take the derivative of y with respect to these weights. I can even take the derivative of y with respect to these inputs. Basically, all the derivative is computing is, how does the output change if I change that particular value a tiny amount. And so the overall function that the neural network represents is differentiable with respect to all of its parameters simply by changing the activation function of the neurons, the perceptrons, to be differentiable. The overall function network itself becomes differentiable. We'll actually derive the actual derivatives using the chain rule in the next class. Okay. So here is the overall setting for learning the MLP. You are given a set of input-output pairs, x and d, where d is the desired output, and x and d may both be vectors. They don't have to be scalars. We must find the network parameters such that the network produces the desired output for each training point, or at least a close approximation to it, and we're going to specify the architecture of the network ourselves. The structure of the network is not something that's going to be learned. Now let's go back to how we actually said we would optimize a network. We said that if you had the entire function g, then you can define an error between the output of the network and the desired function. And then you can compute the average or the average error over the entire input space through this integral. And you would estimate this w such that this average error was minimized, right? Now, you don't need to be minimizing the error over the entire input space. That doesn't make sense. So for example, if this room or if this space, the entire space around us was the input space, and if students are only present in this room, we don't care whether we are making mistakes outside or not. So you don't need to even consider the regions of the space where you're not likely to encounter inputs. So one way to actually account for that is to factor in the probability of x and say that regions where I see x more frequently, the error is more important. Where x is less frequent, the error is less important. Now, if the function is perfectly matched, regardless of what p of x is, in the regions where the data do happen, you will have no error at all. Now, what is this term over here? This is the expected value. You have a function, the divergence between the output of the network and the desired function, right? At x, you're multiplying it by the probability of x and taking the integral. So this is the expectation, the average value of this divergence function over all x, right? So we are defining the expected value of the divergence between the output of the network and the desired function. And what we will really be doing, what we really are doing when we train the network, is to estimate the w's such that this expected value of the error is minimized. Now, if this is unclear to you, stop me, because I'm going to continue on this vein for the next few minutes. Anybody have any doubts about this? Guys on that side? Yes?
Somebody asked from this room, why is it called divergence?
Terminology. I'm not responsible for it. Right? So there are reasons for it, but yes. It is, as far as we are concerned, it's a measure of error between the output of the network and what we want it to be. Okay? So now if this is clear, let me continue on. We don't actually have all the function g of x everywhere. What we really have are samples of g of x, pairs of x and the value of the function at x, many such samples. And if the sampling is good, if you've chosen the samples properly, where we are actually measuring the function, then in that case, if you'd be choosing x's from the actual distribution of x itself. In other words, you'll be choosing more samples where x is more frequent and fewer samples where x is less frequent. And in most cases, this kind of naturally happens. If you're looking at real world data, you will get more samples of more frequent data and fewer samples of less frequent data, so all is fine. So given this is this term on top is the expected value of the divergence between the output of the network and the desired function. Instead of taking this integral over all of x, if I simply computed the divergence at each of my training examples and averaged the lot, this term here is also an estimate of the expectation of the divergence between the output of the network and the true function. So this lower term is the empirical average of the divergence over all of the training samples. The upper term is the true expected divergence. This empirical average is an approximation, is an estimate of this guy. And statistically speaking, this is an unbiased estimate. This, in the limit, you will expect is exactly the same as this guy as you keep having more and more training samples. So what we really do is when we are trying to estimate, so here remember earlier what we did was we were trying to estimate the W that minimized this expected divergence. Instead, we are going to be minimizing the empirical estimate of the expected divergence, which we will call the empirical risk. And so what we actually perform is empirical risk minimization. You don't know the function itself, you just have samples. So you're sort of coming up with an empirical estimate of the error between the output of the network and the true desired function. And that is what we will minimize. You're going to be defining a divergence between the output of the network at each training instance and the desired output at that training instance. You take the average of this over all training instances, find the W that minimizes this. So this is an instance of empirical risk minimization, right? This terminology is only for my pleasure and yours. Fortunately, you don't have to think about it ever, and you can just go ahead with happily with your neural network lives, and it won't change your life one small bit. Anyway, so one thing that you do need to note is that this empirical risk here, which is the average divergence over all the training instances, is only an approximation of the true risk. So it doesn't mean that anything that minimizes the empirical risk will actually minimize the true risk. So this is a guess. We are always taking a guess. This is something that you must keep in mind, right? So here is the problem statement now for how we will train the neural network. You're given a set of training instances where for each instance you have the input X and the corresponding desired output D. For each training instance, you can define a divergence between the output of the network and the desired output. You take an average of all of these guys, and we are going to try to estimate W that minimizes this term, right? It's 9:47. We have 23 minutes more, but I know all of you get fatigued. Some of you are sort of keeling over, so I'll give you 3 minutes to refresh yourselves. If you want to go wash your face, if you want to grab some water, do so. We'll start in 3 minutes. Okay. We don't have a black marker.
And I think yesterday we only tried most of the time. We can try and sort of do different.
How's it? How's the streaming going?
Yeah. You can see like a whiteboard is easily, which the students somehow took a bit of time. Yeah, I was looking at that.
I mean, so far audio seems good, that camera's working, it's just the glare, but that's the problem.
I'll get a black marker for the next class. We should be fine.
We can try turning off all the lights, but then we can try. We tried turning off all the lights, but we thought it was too dark. Now that the sun's up a little bit more, it might make a difference. It totally blacks it out though. Oh, yeah. We need light for him.
For me?
Yeah. No, but Jerry, there's a reflection. The whiteboard.
It's you or the board.
That camera picks up.
I mean, there's no perfect solution, but this is better than nothing, right?
Yeah.
Yeah, this is definitely significantly better than last week for sure. So what happens is when you're drawing on the whiteboard,
because the camera is right here, you kind of cover the diagram when you're drawing it.
Yeah, I try to move out, but yeah, so I'll keep that in mind though.
But we can actually change the camera angle. So just let
No,
us know what's your natural
so no, what I will do is I will, because if I'm blocking it for the camera, I'm blocking it for the students. So I will try to draw proper. Be careful.
So far, it hasn't been bad. I mean, every single time after you have to be there right.
Yeah.
After
when you move it.
I give them like an extra 5 seconds to like read after once you go back to that.
So all right, folks, get back to your seats. Your 3 minutes are up. You're awake, I hope. And if you aren't, you're going to miss the rest of the class because now the fun stuff begins. We're going to look at a crash course on function optimization, which I do not expect to finish today. So Professor Tom Manzini is going to finish it in the next class. But I will begin with a brief revision of the notion of derivatives. Do not look at the screen, right? So blank the screen, everybody. Anyway, can somebody tell me what one means by a derivative? Yes.
Derivative is the limit of the function divided, is the limit of the function to a value divided by the input x.
Anybody else? Can somebody give me yes?
Instantaneous rate of change.
That's a good one. Anybody else? From a purely mechanical perspective, you may now look at the screen, right? So a derivative of a function at any point tells us how much a minute increment in the argument of the function increments the value of the function. But for this specifically, we are going to be assuming if you take any continuous function and if you keep zooming in, eventually the function is going to be linear. So the derivative is literally defined by this term over here. For a small enough delta x, delta y equals some alpha times delta x. This alpha is the derivative. This is the one and only definition of a derivative or decent notation of a derivative. Anything else that you've used is either confusing you or wrong or both, right? Now, so when x and y are scalar, you're just going to write y equals f of x. That's a standard function, right? Now over here, as you keep zooming in, for a small change of x, small change delta x, you have a corresponding change delta y, right? And the two, if they are related by some multiplicative term, alpha, for a small enough delta x, there's a corresponding small delta y, which are related by alpha. This alpha is the derivative, which we will sometimes write, unfortunately, as dy over dx. And I'm saying unfortunately, and you will see why I say this is unfortunate in the next slide. Sometimes we also write this as f prime of x. But regardless of how we write it, we are literally saying what is the multiplicative term that I must multiply an incremental change in x by to get the corresponding change in y. Now let's go to a multivariate function. Y is scalar, x is a vector, right? So in this case, what are we really looking at? You have this function, which is maybe a ball. You are computing the derivative at any point. So at that point, you're really saying, if I change my x by a little bit, by delta x, what is the corresponding change in y? But x is now a vector, right? The notation of dy over dx is nonsense. It doesn't even begin to apply. What you really want to think of is, I have delta y. What is this alpha such that I can multiply delta x by it to get me delta y, right? Alpha is the derivative. Now, if x is a vector, what is delta x going to be? Anyone? It's also going to be a vector, right? It's pointing in some direction. Depending on the direction you choose, it's going to point in different directions. If x is a column vector, what's alpha going to be? Why? Because y is scalar. So if y is scalar, you have to multiply a row vector by a column vector, right? So alpha. So literally, alpha has this form, it's a row vector. And so delta y equals alpha 1 delta x1 plus alpha 2 delta x2. This derives by definition. There's no magic over here, right? This is by definition. This is exactly what, based on the fact that if you get close enough, everything is linear, right? That's how you define the derivative of this particular function at any given x. But then, what is this alpha 1 going to be? What is the actual value of alpha 1? To find out what the actual value of alpha 1 is, you can set all of these delta x's to 0, right? And just shift a little bit along delta x, because this equation is generic. It doesn't matter which direction you're moving in, so long as the delta x is small enough, right? So that means if I set all of the other delta x's to 0, then I'm going to have correspondingly a delta y equals alpha 1 times delta x1 when the remaining x's don't change. That is what we will call our partial derivative of y with respect to x1, right? You have encountered this. Now the difference, we have a difference in notation. We like to use this rounded d, the dou. When we represent partial derivatives, we write full d when we represent complete derivatives. Regardless, this a over b notation is confusing, because when you're actually looking at derivatives of scalar functions with respect to vector variables or vice versa, things don't work out quite so cleanly. Now, another thing, typically we will write this as delta y equals this term, which is a derivative of y with respect to x. Note that I'm not writing it as dy over dx times delta x. This guy is what we will call the gradient of y with respect to x. Now here, there is a little notational inconsistency amongst the various textbooks. I am choosing a specific notational notation. How many of you are familiar with the term gradient? And how many of you have thought of a gradient as a row vector? When you think of a gradient, you're always thinking, if it's a function of a column vector, the gradient is a column vector, right? If you thought of the vector as a standard column vector, how would this notation be? How would it change? You would need a transpose, right? I'm not going to be transposing things, as you will see. So in this notation, my gradient is a row vector where every component is a partial derivative of y with a corresponding component of x. Just a notation, okay? Now, all right, let's go back to the business of, now that we've introduced derivatives, we'll come back to this again. Let's go ahead. Although everything that we spoke about was about optimizing neural networks whose parameters are weights, which we have represented by w, in the slides that follow, I'm going to be talking about generic functions of a variable x, because I'm speaking of the general problem of optimization over here. But that x must be replaced by w when we begin dealing with neural networks, all right? Okay. So let's say, what is the general problem of optimization? You have some function f of x, which might be like this curve, and you're asked to find the value of x where f of x is minimum or maximum, depending on the problem. But let's assume we're considering the minimum, right? So if it's a scalar function, you want to find this location. A function of a scalar variable, you want to find this location where the function has the absolute global minimum. If it's a function of a vector variable, you want to find this one location where the function has its lowest value. Or if it's something more hideous like this, this is the point at which it's at smallest. You want to find this value. How do you go about this? You've done this even in high school. So if I were to ask you to find the location of a minimum, what is the standard approach? You just take a derivative and you'd equate it to 0, because a property of a minimum is that generally it's a turning point. What we mean by turning point is that if you stand at that point, no matter which direction you walk in, the function value is going to increase, right? So at that point, the slope is 0. But it's not sufficient to just say the derivative is 0. If that is, the derivative is 0 at both minima and maxima. So what is the next check that we use? We look at the second derivative. So you know, if you both maxima and minima are turning points, and the signs over there show you the signs of the derivative in each case. Here, as x increases, the function increases. Here it decreases. Here again it increases. Here again it decreases, right? So, but then something interesting happened over here. If you, that is the derivative. The derivative was positive until this point, then it became negative. Then it swung around and became, it stayed negative till that point, and then it became positive. Stayed positive at the next point, it became negative. So if you look at the derivative of the derivative, it's going to look something like so. At minima, the derivative is going from being negative to positive. So the derivative of the derivative is going to be positive, right? It's gone from being negative to being positive. At maxima, it's gone from being positive to being negative. So the derivative of the derivative is negative. So you just check your second derivative, and you can decide whether it's a local, it's a minimum or a maximum. The problem, of course, is, yeah, right? That, but before I continue, if you look at derivatives of the function of a single variable, the derivatives can be 0 at various points. They can be 0 at maxima, which are turning points. They can be 0 at minima, which are turning points. They can also be 0 at inflection points. Inflection points are by definition points where the derivative is 0, but which are not turning points. So in this case, this is an inflection point, right? It's flattening out, but then it continues in the same direction. So here, these are local maxima. If you look at the derivatives, these are all 0. But observe what happens at the inflection point. It doesn't cross, the second derivative doesn't cross 0. It just stays below 0, right? All right. So the second derivative is greater than 0 at minima, less than 0 at maxima, and 0 at inflection points. It's a little more complicated for functions of multiple variables. But for us, what if you have, so anyway, for functions of multiple variables, this was for a single variable, right? For functions of multiple variables, the same principle still applies. If I want to find a minimum, the minimum is still a turning point, meaning it doesn't matter which direction you walk in, the value of the function is going to increase. So we must find a point where shifting in any direction by a microscopic amount will not change the value of the function. That is what we mean by saying that the derivative is 0, which means that if you actually computed this gradient term, every single term in it must be equal to 0, right? Now, let's go back. We've already introduced the notion of a gradient. What was the gradient? How did we define it? We defined gradient in terms of this guy, df equals, gradient times dx, right? But then specifically when you looked into the gradient was the set of partial derivatives of the function. What can you tell me about the direction? This is a vector, right? The gradient is a vector. What can you tell me about this vector? Does anybody know what this means, what this vector represents? Anyone? You must be knowing, right? You're just keeping quiet. The direction in which changes the most. So let me explain why. This is a vector in a product. The gradient of x times dx is a vector in a product because this is a vector and this is a vector, right? So let's look at the properties of vector inner products. Consider the inner product between two vectors u and v. So what is u transpose v, or the inner product between u and v? Is the magnitude of u times the magnitude of v times the cosine of the angle between the two vectors, right? So at what point, when will this inner product be maximum given that the magnitudes of the two are fixed? When theta is 0, when u and v point in the same direction, right? So now consider what happens for this equation over here. df equals the gradient of f times dx. It is the inner product between the gradient and x. If I fix the length of the step dx the length of the then, and if I decide in that case, right, when is, and so I give you the gradient, and I allow you to modify dx. So the gradient is fixed, it's just the set of partial derivatives. If dx keeps swinging around, I keep the length, but I rotate x around. At which point will this inner product be maximum? When the angle between the two is 0, right? So in other words, the gradient is the direction in which dx must point for the function to increase fastest. That's when dy is going to be largest. Get that? Right? So the gradient is literally the direction of the fastest increase in the function. dy equals gradient times dx. If I give you the gradient, dy is going to be largest if dx is in the direction of the gradient. So the gradient is the direction of the in which you must travel for the function to increase fastest. So over here, if this is my function, this is going to be the direction of my gradient, right? Although I can walk in many directions and increase the value of the function, this is the direction in which it's going to increase fastest. And so moving in this direction increases it fastest. Moving exactly opposite to it in the direction of minus delta x, minus gradient of x, is going if I do that, that's when the function will decrease fastest, right? And at these maxima and minima, the gradient is going to be 0. What this means is that it doesn't matter which direction you walk in, the function value is not going to increase. Now there are two things that turn out over here. First, the direction of the gradient is the direction in which you must walk fastest. You must walk for the function to increase fastest at any point. What about the value of the gradient? What does that tell you? Anyone? The value of the gradient is actually going to tell you what dy is for a given length of dx. Meaning if the magnitude of the gradient is greater, the function increases more rapidly, right? So at this point, the function has some rate of increase. It's going to increase fastest when I walk in this direction. At some other point, say over here, it's going to increase fastest when I walk in this direction. However, the rate at which the function increases for a small step is much greater here than over here. So you expect the gradient at this point to be greater in magnitude than the gradient at the other point. Right. That come across? So if you don't have questions, I'm going to assume that you understood this, right? And it's going to turn up in either in your optimization or in your quiz. So now, here's something else that we will often use. If I have a function, I can always draw a level curve. A level curve is, I have this function. I can slice it at any height. If I slice it at any height, I'm going to get a contour. That contour is a level curve. And here's the magical thing. The gradient is always going to be at 90 degrees to the level curve. It's very trivial to prove. So so at any point, the gradient is also the direction that's perpendicular to the level curve, and it shows you the level curve. Now, you can also define something called a Hessian, which is the second derivative of a function. So if I have some function of many variables, the Hessian is simply the matrix of second derivatives. I won't go over this right now. We will encounter it again later in class. Now, let's return to our problem of optimization, right? Now that we've defined derivatives and defined gradients, the optimum point is a turning point right here. That's where the gradient is going to be 0. Now, we said we could just solve for the optimum point by equating the derivative to 0. So in which case the gradient is going to be 0. We want to check if the second derivative is positive for this to be a minimum. In the case of a vector, function of a vector variable, the second derivative is a Hessian. What you would actually do is to compute an determine if this Hessian is a positive definite matrix. In other words, if all of its eigenvalues are positive, and then you decide that it's a minimum. On the slides, we actually have an example of this worked out. But the problem is, very often it's simply not possible to compute the gradient at any point, equate it to 0 and solve for it. And a neural network is one such problem. The the gradient doesn't have a nice closed form. You can't just write the gradient as a function of the weights, equate it to 0 and set it to 0. That's not going to work. So in this case, you're going to need an iterative solution where we will begin with a guess for the optimal x and refine it iteratively till the correct value is achieved. So what we will do is we're going to start at some initial guess x0. Now at that x0, you will look at the current slope. If the slope is positive, what does this tell you? It tells you that if you move forward, the function is going to increase. So when the slope is positive, you want to take a step back. If the slope is negative, it tells you that if you go forward, the function is going to decrease. So if the slope is negative, you're going to take a step forward. And so you will start from some initial guess and update the guess towards a better value of f of x. Basically, keep updating your x such that f of x keeps decreasing till f of x no longer decreases and you can arrive at a minimum, right? So questions are which direction do you walk in and how big must these steps be? So here's the iterative solution. Start at some point, find the direction in which to shift the point to decrease the error, which can be found from the derivative. If the derivative is positive, in your case, you want to move left in that direction. If the derivative is negative, you want to move right, and that will decrease error. Or I can rewrite it in terms of arithmetic. I can initialize my x at some x0, and while the derivative is not 0, I can check the sign, and if the sign is positive, I'm going to take a step backwards. Step is always a positive number, x minus step. If the sign is negative, I'm going to take a step forward, right? Or I can rewrite this again like so without a check. I can simply say xk minus sine of this guy times step. So if the derivative is positive, this is 1, in which case I'm taking a negative step backwards. If the derivative is negative, this is minus 1. Minus 1 times a minus, this becomes a plus. You will be taking a step forward. Or I can shrink it further and simply put the derivative right in, right? Why do I just have to extract? Because there's this magic step thingy out there. Why do I need to write it separately? So now I can just say at each point, take a step eta proportional to the derivative. This automatically takes care of the sign of the derivative as well, right? All three of these are the same algorithm. I just wrote them differently. Nothing has changed. And so this is our gradient descent. This is our iterative solution for finding the local minimum of the function. When it's a function of a vector variable, I have to change it slightly. Instead of just looking at the local derivative, I'm going to look at the gradient. But now observe that I've used the transpose just to keep the notation consistent. But you get the idea, right? So this will automatically take care of walking in the correct direction in each case. You will start at some point, and then iteratively, you will, if you're trying to find a maximum, you're going to walk in the direction of the gradient because the gradient is the direction of maximum increase as we saw. If you're trying to find a minimum, you're going to walk opposite the direction of the gradient because the negative of the gradient is the direction of maximum decrease. So this is the gradient descent algorithm. Now, what exactly is the step size? We'll get to that in a later class. When do you stop? As you keep taking these steps, the function is going to keep decreasing. At some point, the change in the function between consequent steps might be so small that you can decide that maybe I'm in the flat region. Or you could just look at the derivative. If the gradient is too small, you stop. There are many different criteria that we can use when we actually for deciding when we're going to stop. So here's the overall gradient descent algorithm. I'm going to stop right here, which is you will initialize the variable x that you're trying to minimize the function with respect to, and while some termination criterion has not been satisfied, which is to say while the difference in the value of the function between subsequent steps is greater than some threshold, I'm going to keep walking against the gradient in small steps till I get to a point where I've hit the minimum. Right? In the next class, we'll pick up from right here and see how this is going to be applied to train a neural network. In other words, we'll be talking about backpropagation. Questions? Yes?
Does the step size has to depend on gradient, or can we also use something else in addition to the gradient?
So we'll talk about these in a couple of classes from now. In fact, we will be addressing this in 2 classes from now. Right? Okay, thank you everyone. See you on Monday.